Today we are going to present our first lunch and learn session ever, which is on Adams. Now to tell you a bit about the lunch and learn and sharpen the saw sessions we've got. So it's going to be one of each per month, usually well, I actually forgot the exact timing of it, but for the, first or second Saturday, whatever, but you see there on the right-hand side, the planned lunch and learn sessions that we've got scheduled for the rest of the year. The sharpen the saw sessions will still needs to be confirmed, and they will be, dates will be made available at a later stage. So the difference between a sharpen the saw and lunch and learn. So the lunch and learns will be the ones where we try to bring in our partners from Hexagon so that they can discuss and tell you about the latest updates, tell you what's new, just get the excitement going again for the product. So this will be good both for existing clients as well as new clients and people that are interested in the specific software. So don't think just because you are not currently using a certain software that it might not be of interest. Maybe there's something worthwhile you notice, something that they mention. On the other hand, the sharpen the saw sessions will be more technical, will be more hands-on. So that will usually be driven by one of us from Simtech Engineering. It will focus more on the technical side, as I said, and be a bit more about the nitty-gritty details, how to do something, how to use the software more effectively, or anything in that line. So what I can ask you, if you haven't done so yet, is to just go fill in our lunch and learn and sharpen the saw questionnaire. So we put this out there to determine, how much or not how much, but whom of you out there are interested in what fields, what subjects, and when, and just basically just determine what you want to know about. This is also how we determine what we're going to talk about in the sharpen the saw sessions from this questionnaire. So please, if you haven't done so yet, please go complete the questionnaire. We'd really appreciate it. If you have done so, thank you very much. It's thanks to you that we've set this all together and we've started doing it. So I've got on the here with us today Marceliano Fumero from Hexagon. He is our resident Hexagon Adams specialist, and he's gone ahead and prepared a couple of slides for us to tell us, what's new, what's exciting, and what's the latest news from Adams. Marceliano, please.
Absolutely. Thank you very much for the introduction, Benja. I'm going to put my camera now. I feel odd when I'm talking to an empty. Yeah, thank you very much for inviting me. It's a pleasure for me to be here and have the opportunity to present Adams, to tell you a little bit about what it is for those who don't know Adams already, and to tell you, more importantly, the key developments that are the focus on the product team, and why we're focused on those developments, why we believe that those implementations will take Adams to new and more exciting places than it is now. So we are a relatively small group today. So I think that gives us the opportunity to maybe do a quick, very, very quick round of introductions. If you don't mind me asking, one thing that I would like to know from you, it's primarily what experience do you have with Adams? Is it the first time you hear about the tool, or do you have any experience with it, potentially hands-on experience? Depending on the overall knowledge that we have about Adams, I might actually go very quickly through the introductions and focus on key developments. Or if you are new to the tool, I'll make sure that we all understand what Adams is and what we're talking about, really. So I'll kick that off myself. My name, as Benja said, is Marceliano Fumero. I am the business development manager for System Dynamics, which is the division of Hexagon that deals with Adams specifically. and another tool that you might have heard called Romax, which is dedicated for driveline design. I don't know. I would like to hand over to. I'll check the list and call you one by one if you don't mind. I think I have Dewald in the list as my first person.
Yes, thank you, Marceliano. Yeah, so good afternoon to everyone. My name is Dewald Hatting. I am currently a postgraduate student at the University of Pretoria. I'm also doing some assistant lecturer work on a part-time basis. At the moment, I'm full-time employed at Milcor, but I'm doing some AL work part-time. So in my case, Adams is something that I'm looking to use for the postgraduate dynamics module that I will be presenting in the second semester. Just perhaps with regards to my experience with Adams as well, I was fortunate enough to have a bit of an introductory session with SimTech. I think it was at the end of last year. And from what I've seen, the ability of the rigid and flexible multi-body dynamics is something that I'm really interested in incorporating into the module that I'll be presenting.
Oh, excellent. Thank you very much, Dewald. I'll move on to Garrett.
Hi, I'm the technical director at SimTech. My specialist field is more in FEM and CFD, but I have used Adams, not a lot, but a reasonable amount. So I'm definitely not a specialist. Benya knows a lot more about it than I do.
Oh, excellent. Chris?
Yes. I'm the CTO at a company that does development of military vehicles. I've been using, or I used to use Adams quite a lot. Benya was one of my previous colleagues, and so I think I started using Adams in 2000. In 2000. Before that, I used DADS for a couple of years. Haven't been using Adams a lot lately, but I'm very interested in seeing the new developments.
Oh, excellent. Absolutely. Thank you very much for that, Chris. We just received a message from Kat saying that she can. That's fair enough. No problem at all. Yeah. If you could leave us, please, just a comment about your level of experience with Adams on the chat, that would be useful, but completely understand. So the last person I have in my list is Jonathan.
Hi, yes. Yes, Jonathan Odengan, currently working at ADG Mobility as a simulation engineer. So currently working with Adams, FEA, CFD, a few different Hexagon software. And yes, so we specialize in protected mobility. So Adams obviously can play quite a big role in that. And then also a postgrad student at the University of Pretoria. Yeah.
Oh, brilliant. Okay, thank you very much for that introduction. So we have a bit of a mixed audience, so I think the contents that we have today are all appropriate for what we're going to discuss. I will share my screen now. Oh, thank you very much, Kat. We just received your, okay, you have experience with Adams as well. That's really good to know. Excellent. So let's crack on then. For the presentation today, what we have in the agenda is fairly straightforward. I'm going to start with an overview of Adams and multibody dynamics in general. It does sound like all of you, to some extent, know what multibody dynamics is, so I'll race through that to some extent, but just making sure that we highlight content that is basically context for what the new developments are. From there, the main dish of the presentation today is the key areas of development. And we don't have a dedicated session for use cases. I will introduce a number of use cases throughout the presentation just to illustrate the point of what these capabilities actually do in real time when appropriate and when we actually have a use case to share. One thing that I forgot to say, I'm based in the UK, so it's 10 a.m. for me, but this is a lunch and learn. So if you are indeed having lunch, bon appetit. Questions, please, at the end. If you want to interrupt me at a specific time to make a question, that's valid as well. So let's get started. First of all, what is multibody dynamics? So this, I think, is very straightforward to you, but I'll do a very quick recap. In my view, multibody dynamic at its core, it covers three specific areas of analysis. One of them is evaluation of motion. As you might know, if you have a mechanism in a CAD file, for example, studying motion allows you to see if there are collisions or if the kinematics of the system actually allow the system to do what it's meant to do, whether it is an actuator, suspension, etc. I think this is how multibody dynamics was born, and then it evolved into what's probably the main usage of multibody dynamics these days, which is load distribution. When you have a system like a vehicle, for example, the loads that come through the road or the excitation from the driveline, they propagate throughout the entire system. And it is important to know what are the specific loads in every single component that the system has, because this is the only way that we can size and design the components appropriately for durability purposes, MBH, etc. So this is probably the biggest area of application for multibody dynamics, and Adams, of course, being part of it. And a bit of an advanced usage of Adams is understanding system interactions. So we're talking about interactions that are of a dynamic nature, maybe interactions of natural frequency in different components that can actually trigger problems in the behavior of the system. And these are really difficult to predict until the whole system is put together. So Adams is multibody dynamics. It is a pretty good way of basically predicting problems that could arise from those interactions, and obviously evaluating changes to the design that can fix those problems. So those three things, from an application point of view, usually lead to either improving the process of defining a conceptual design for a product, reducing prototyping. Once you go after the conceptual design and you have a system that works, you need to evaluate it. Traditionally, you would do that with prototypes, but we see lots of our customers actually eliminating some of the specific test campaigns that they use, because all you have to do is basically make sure that the model is a faithful representation of the product, and then you can perform the same tests in the virtual environment that is quicker and cheaper. Durability and MBH analysis. So this is, like I said earlier, deeper or more complex applications of multibody dynamics to find solutions to problems that involve system interactions. And finally, and this is probably one of the biggest areas of growth for us at the moment, is control design. Actually, not control design. Multibody dynamics is not a tool for the design of controllers, but the multibody dynamic models are ideal for evaluating if a controller works or not, basically. Instead of plugging your ECU to a machine or to a vehicle, to a product, you just connect it to a virtual version of the product, where you can perform as many tests in parallel as you want, or do all the calibration and check the measurements of physical variables to see that your controller delivers the requirements, essentially. So everything that I've said so far could be said about any multibody dynamics tool, and as you might know, Adams is not the only one in the market, but it is the #1 tool in the market for this. And the reason why it is the #1 tool, well, I think there are many reasons, and part of what we're going to discuss today hints into that. But I think the main reason is heritage and legacy. So Adams is the oldest multibody dynamic tool in the market. We say that it has over 40 years in innovation, but we know we're very close from the 50th anniversary, which we're looking forward to celebrate. And obviously 58 years of development translating to a maturity that allows us to cover many different applications in many different industries. And this is really what differentiates Adams from most other software in the the market. A few specific, not testimonials, but projects that went well and we take a lot of pride on are, we have a use case with Airbus in which the European Aviation Safety Agency actually allowed Airbus to replace physical testing on wings with virtual testing using Adams. And this is a type of test that involves safety of the passengers. This is basically to ensure that when the wings are bent, all the actuation systems still work as intended. So the fact that Adams was trusted to replace real testing in real life for that is a big thing for us. The trust that the automotive industry has placed in Adams is something that we're very proud. I think we say that 24 out of the top 25. I don't know if that is still an updated case, but all the new players coming into the automotive world seem to have an interest or directly be using Adams already. So that's a big thing. And this is a bit of an oldie, but something that we're very proud of. Adams was used to replicate the landing procedure for NASA JLP, the Curiosity rover campaign on Mars. And this is interesting because this is something that couldn't be tested in real life because obviously the atmospheric conditions on Earth are very different from Mars. So they had to rely on this virtual test in order to make design decisions. And the campaign was a success, as we all know now. So knowing that Adams had something to do with it is something that we're very proud of. But enough with the bragging. So now I'm going to start talking a little bit more technical about the product. If you haven't seen Adams yet, and even if you have seen it, this might not be evident. Adams is not a standalone tool. Adams is actually a suite of products. And that suite covers solutions for creating multi-body dynamic models, including flexible bodies. It includes tools that are dedicated for the integration of models that are not inherently mechanical, okay, such as controls or multiphysics integration when we have loads that are generated from fluids or pneumatics, for example. We can integrate that into the entire simulation, obviously with a focus on understanding the mechanical design. But still, those boundary conditions are important, and these tools allow us to do that integration. And then obviously, once you have a model, what you want to do is run it, post-process the result, and that's how we get insights. So we have specific tools for the analysis of the data in order to improve durability, acoustic performance, MBH. All of that is Adams altogether. And I would like to very briefly go through what those products are, simply because when I start talking about the key developments, some developments are focused on some specific products. And it's good to know what we're talking about, basically. So I will start with the tools that are dedicated for modeling specifically. We have Adams View and Adams Modeler. These two are almost exactly the same, but with different GUIs. So Adams Modeler was released with the intention of replacing Adams View. It's a modern-looking, more intuitive interface for Adams. But we have so many existing users that just love the Adams View interface that we had to actually keep it running in parallel with Modeler. So if you've never tried Adams before, I recommend you to go straight into Modeler. It should be easier to learn. But if you're using Adams View and you like it, it's there and it will be there for the foreseeable future. We have Adams Machinery. This is actually an add-on, but it's interesting for mechanisms that are typically found in many different products, like electric motors, gears, bearings. Adams Machinery allows us to generate the models almost automatically based on parameters. So you don't have to have a CAD or you don't have to have geometrical data to create those models. As soon as you provide the type of data that you normally get from a data sheet of the product, the software will generate the model automatically, and then that can be integrated with the rest of the model of your machine, your vehicle, your aircraft, whatever it is. And finally, for the automotive world, we have Adams Car. It's one of the biggest seller tools that we have. Essentially, it provides templates for stereotypical assemblies of suspensions, chassis components, drivelines, and even vehicle bodies that can be easily assembled and customized to generate entire vehicle models, which otherwise, if you were trying to generate from something like Adams View or Adams Modeler, it could be done, but it would take a considerable amount of time compared to this. So the idea of having these different interfaces to offer the possibility to model pretty much, or do the modeling in a generic way that allows you to model pretty much anything that moves, or a highly productive way of modeling systems that we all know pretty well. In addition to that, for all of these tools, we have what we call horizontal capabilities, and this is where integration comes in. We have the ability to integrate flexible bodies when the flexible body is expected to have a strong impact on the behavior of the system. We have the ability to integrate controls. So you can take what typically controls are modeled in 1D. I'm not sure if you're aware of that, but 1D offers a pretty good platform to model both the control logic and the actuation system, whether that actuation system is electrical, pneumatic, or hydraulic. So once you have that full definition of how the controller works, you can plug it into the mechanical part of the system, which is what we do in Adams, and then you have a full representation of the product in the virtual world. Equally, we can actually take that entire system and export it into what we call real-time simulations. I'm not going to talk a lot about that because a big part of the development of 2024 and 2025 are related to real-time. So we'll be going through that in a fair amount of detail in a few moments. We have tools for advanced co-simulation. This is where we leverage our relationship with other tools like Actran, Cradle, etc. And this is mainly to define, most cases, boundary conditions. We have the ability to, for example, in heavy machinery, to characterize solid to soil contact in order to have a good dynamic definition of how operating conditions like the one in this video will be. We have the possibility to introduce aerodynamics or fluid loads that affect the behavior of mechanisms, as we can see in this little video there. And then within the model itself, within the mechanical model, we have the possibility to integrate non-linear deformations. For example, this is a window going through the rubber that covers the window in a vehicle, and the resistance of that rubber is highly nonlinear. Characterizing that in Adams requires the multibody dynamic aspect of it and the nonlinear behavior in order to get a good representation of what is happening. So that covers everything that is related to modeling. And then, like I said, we have tools dedicated to the analysis of those models. In its basic form, we can animate the system. We can plot the transient results in order to get insights to what is happening. This is pretty much like looking at the results from a real prototype in a test bench. We have tools that are dedicated to doing durability analysis. Vibration analysis, once again, I'm going to be talking a little bit more about vibration and acoustics later. So if you didn't know, this is something that multibody dynamics also cover. And once again, it's an area of focus at the moment, or growth when it comes to the development of the product. So that takes us to what are the key developments in Adams for 2025. I say 2025, but some of it, especially the real-time conversation that we will have also covers 2024. This is something that has been evolving very rapidly over the past couple of years. But it's still in a phase where lots of customers are just finding out about it and adopting it. So I think it's a good opportunity to talk about that. All right, so there are 3 key areas of development that I'm going to cover today. The first one is Adams going into the cloud, and this is probably the newest thing that I will be discussing today, because it's something that we never did before. Up to now, Adams is on your machine and nowhere else. The intention, like with many other software, is to move a lot of this capability into the cloud, eventually giving you access to Adams fully through a website. But we are not there yet. So today I'm going to explain what this initial implementation of Adams in the cloud is and how it can help increase productivity, agility, and collaboration. Then, like I said, I will discuss in more detail what Adams in real time means and how you can use it for the benefit of improving the design process and reducing prototyping. And finally, Adams for MBH. This is not new to us. This is something that is being done for quite a while. But because MBH, acoustics, vibration, requires higher levels of fidelity in the model, and in some cases capturing complex physics in the model, it's something that it's always evolving. Essentially, customers keep coming back with new challenges for us, and we basically implement new features to make sure that we can use Adams for whatever our customers need. So I will be covering a few specific developments that are aimed to improve not the accuracy, but the fidelity of the models that we generate in Adams. So let's dive into there. First of all, I'm going to talk about Adams in the cloud, and this is funny. This is a video that is about to be released online. You're the first ones to see it, and it's just a teaser to what is coming. So coming soon, to be very specific, means, if I remember correctly, I think it might be the 17th of next month. So it's very soon, less than a month away from the release of this capability. Oh, sorry, move forward. So what's Adams in the cloud? I don't know if you have heard about Nexus so far. I'll show you very quickly what that is. Nexus is the portal that Hexagon has been developing over the past few years to interact with the customers online. So if you are a customer of Hexagon, you should be able to access this site and sign in. And in there, you will find lots of things, really. You can download any software you like. If you don't have the licenses, obviously, you cannot use it, but you can request licenses through the site and initiate a sales conversation with us. You have documentation for the software. Let's see if I can find the product, maybe. Oh, lucky for me, Adams is one of the first ones. So if you go to the Adams site, for example, this is where you can see a bit of information about what it does. It will give you a link to our documentation center. It will point you towards other tools that closely relate to Adams. And it will give you access eventually to Adams Compute, which is what this implementation is all about. So Adams Compute, to put it simply, it's just the ability to run models from Adams on the cloud, okay? So what happens here is Adams is still a desktop-based tool when it comes to creating models. But normally in Adams, you hit run, and then you use the course in your machine to run the model, and then you review the results in there. With Adams in the cloud, what you can do is click run, send it to one of our servers. The model gets run in there, and the results are sent back to you. I'll tell you in a minute why that is useful. But before I get there, the other thing that you can do at the moment with Adams Compute is to take the results, and instead of doing plotting with the Adams post-processor, we have dedicated post-processors on the cloud that can be used to manipulate the data that the model will generate. So why is that useful? Well, let me show you the 3 applications of this. One thing is what we call just run it. I want to show you a quick video of how it works. So as you can see, in the next release of Adams, you will have this Nexus button in there. If you have a Nexus account, you can log in. You can have a project or a place where your data and your models will be saved. And then from Adams in your desktop, you can send or submit your works into the cloud. So this is very similar. If any of you has ever used a high performance computer that is installed as a server in your organization, this will be the same, but instead of going through an internal server, it goes through our servers. And essentially we will charge for the amount of time you use the server. That's it. In a situation like this one, the one that we're looking at in the screen, where you are simply running your model in Nexus, the only advantage you get is that if you have a model that takes a long time to run, and as you know, especially when you include flexible bodies, models can take up to hours to run. You know, your machine doesn't have to be locked in the simulation. If you send it to the cloud, the machine is free for you to continue doing modeling work, anything you need. And when the model is ready, it's sent back to you. Also, the high performance computers that we have in the servers obviously will reduce the running time considerably compared to a normal desktop or a normal laptop, which is what we normally use. And as you can see, sorry, I missed something from the video while I was talking. Yeah, the results can be retrieved back and analyzed in Adams just like you would if you were running in your own machine. So it's not a major disruption. It's just a tiny step simply to make sure that you don't lock your machine there. This is useful, but this is very useful DOE. So now when it comes to DOEs that you have multiple rungs, running in high performance computers gives you the ability to make many rungs in parallel. And if you have a big study with large number of runs, this can reduce the overall time of getting the results dramatically from maybe days or weeks to hours. So as you can see in the video, when we run it this way, the model is sent to Nexus and all the parameters in the model become available in the Nexus interface. So in there, you can decide which parameters you want to use for your design of experiments, which is what is happening right now. You can define, just like in any optimizer or design of a studies facility, the maximum value, minimum value, the type of how you want to use the data. And once you define the scope of your study, which is about to happen very soon in the video, you move into defining your objectives or the outputs that you want to generate from this study. In this case, we call it KPIs. And this is what is happening here. This study is not an optimization as far as I can remember, so there is no lighting hypercube. It's a design exploration, so there is not an optimization objective. It's simply the outputs are defined to define the scope of the study. Now let me stop here for a second. This is how it works. Once you define your study, inputs and outputs, as you can see here, you get to choose what type of hardware you want to use. And we have different solvers. Different solvers will consume different amounts of credits. This is how we basically charge for it. And you know, if the study is really big and it can benefit from having many cores, selecting the right hardware will reduce the overall time spent in running the simulation, and it will reduce the consumption or how much you pay. If the study doesn't have many rungs, but the model is heavy, it's difficult to solve, you might benefit from having a machine that has less cores but higher computational power. So that's why we have the opportunity to select the hardware here. And you have the opportunity to select the maximum running time, because if for whatever reason the combination of parameters leads to the model getting stuck, essentially not solving, you might have a model there in the server, you know, stuck for hours that is actually not producing information. So you can make sure that that's constrained by defining the maximum runtime per run. This will tell you exactly how much credits you need to run your study, and then you can hit run and gather your results. And obviously you will have parts of the interface will show you or monitor what is happening with your work. It might be queued if there are other works already in the queue. It might be processing, and when it says success, then the data is already saved for you. And once again, that data that you generate can be sent back to Adams for post-processing, or it can be used in the analytics part of Nexus. So now the analytics part of Nexus is interesting because this is agnostic to Adams. So essentially this facility, which is only for post-processing data, it's the same for everything for Adams, Actran, Nexus. And what that means is that if you submit a model into Nexus, someone who doesn't really know how to model or who doesn't have any experience with Adams can still use that data in order to assess whatever they need to assess in order to make engineering decisions about the product. So it's a great way of sharing the CA work with people who are not necessarily experts in simulation. I'll stop this here because there's nothing interesting here. All you will see is a bunch of different types of plots that we can produce, which are really nice, but without context, they might not mean much, I think. Okay. So with that said, this is what Adams in the Cloud is all about for the time being, is about increasing productivity by freeing up your machine and accelerating the time to get results. Same thing with DOEs, but in the case of DOEs, this is more about agility. Typically, our customers don't do DOEs every other day, but when they have to do it, then they might feel constrained by the computational power that they have available. So this is an easy way to say, okay, if I have to do a DOE, I'll just get my credits, submit my work, get my results, and I don't need a high-performance computer, or I don't need to install Adams in a high-performance computer. It's that simple, basically. And once you use it, if you don't need it anymore, you can forget about it. And the analytics part of Nexus is all about collaboration, really. It's basically providing an agnostic place where all the engineers, whether they have simulation as their background or not, we can look at results and make decisions together. Okay, so now we will jump into the next topic, which is Adams in real time. What we're seeing in the video is actually a simulator where the forces applied by the simulator are being calculated with Adams in real time. What is real time? What is Adams real time? So if you're not familiar with the concept of real time, you will know, though, that when we simulate events that belong to the real world, if the model is complex, like the one we have in the screen with many components, very complex contacts, and flexible parts, it is likely that the time to simulate the event will be much longer than the duration of the event itself. Opposite to that, if you have a very simple model like this one, where you have a flap that goes back and forth, it is likely that the time to simulate it will be faster than the duration of the event itself. Real time is about matching simulation time and the duration of the event that is being simulated. And the reason why we might be interested in doing that is to connect the virtual world with the physical world. So examples of that might be what we just showed to you, simulators, where you as a user of the product can interact in real life with the product, generate data. Evaluation of ECUs, and this is something that it's confusing. ECUs in nature use digital technology to do their computations, but the inputs and outputs are analog, which means that they are real-time inputs, real-time outputs. So if you want to connect a real ECU with the virtual world, you need to have a model that can run in real life, in real time, just like a prototype would. And we have some cases, I'm going to talk about this in a minute. This is a little bit abstract, but once you see it, it's very interesting, which is characterizing the system using models and real parts of the system working at the same time. So let's dive into that. But before we get to the applications, I'll explain what the implementation of Adams real-time is. So essentially what we did was implementing the real-time solver. And this is a solver where we have increased the performance, reliability, and the way the model is solved in order to make sure that the model solves at the same time with the wall clock, okay? And that it does so without breaking throughout the simulation. Another implementation that was necessary to get this done was what we know real-time FMUs. If you're not familiar with FMUs, I recommend you finding some information about it. It's essentially a standard to connect models from different sources together, dynamic models. So there are specific rules that apply to connecting models that run in real time. And yeah, this is the implementation that allows us to take a model from Adams and mix it with other models and systems that work in real time. And that leads us to the applications, okay? I think the main application of real time in reality is controls, okay? Like I said earlier, if you want to evaluate whether a controller works or not, typically you have to connect it to a prototype and perform certain tests, right? With Adams, you can do those tests virtually. So you have your real ECU, you connect it to one of these machines called hardware-in-the-loop machines. And what they do is translate analog signals into digital signals that the model can interpret. And then the signals from the model, which are digital, are translated back into analog and sent to the ECU. So that's how we establish the connection between those two. And by doing those connections, you can do testing in the virtual world. So an example of that is JLG. This is a company in the US that deals with these machines that you can see over here. They are called telehandlers. And what they do is probably in construction sites or in electrical cabling in the street, you have seen these telehandlers basically get the workers close to whatever they need to fix and then bring them back, or materials as well. So with telehandlers, according to what JLG explained to us, whenever you make a change to the design, you need to reevaluate the control, because the control is what makes sure that the thing doesn't flip when it is in operation. And apparently this is something that happens very often before they release the design. So they said that by having a correlated model in Adams of the telehandler, they can make modifications to the design and simply run the tests, which they have already automated online with the ECU, to make sure that the controller still does what it needs to do. And they managed to reduce the time to do those tests by 90%, which is not a surprise because they have to run many tests. And in real life, each test requires a very complicated setup, whereas in the virtual world, you can just run them automatically, and you can run them overnight, and there's no need to set up anything. So for them, it's a really big deal. It's something that has managed to help them reduce quite drastically the lead time for the delivery of new designs. Another application is what I mentioned earlier, which is what we call hybrid testing. In this case, for example, you can have a drivetrain that is connected to a test bench with a big electric motor. And then this big electric motor will simulate the loads from a vehicle that is being simulated in Adams. So to explain to you how it works, the best use case is one that a public use case we have with Ford, where they told us that they have a single driveline that they use in many different cars. And they said the driveline, the design doesn't change, but the calibration of the controller is very different. So if we wanted to do the calibration in each vehicle, we need to generate a full prototype of the vehicle and test each one individually, which is, as you might expect, very slow. But with Adams, they can simply connect the drivetrain to an electric motor, like I said, and then just change the vehicle that is modeled in Adams and do the calibration virtually. And once again, this is something that helped them save a huge amount of time in the calibration process of their drivetrains and significant reductions in prototypes, because from what I understand, the prototypes were simply used to validate the design and not for calibration or verification. And finally, another application of real-time, which is quite sexy in my opinion, is the use of driving simulators. We have a couple of use cases where the driving simulator is being used actually at the conceptual stage of design. In this case, trying to capture subjective feedback from end users at that early stage. And this is quite important for suspension design because the feel of the suspension is part of the signature of the product. And usually it's the thing that you evaluate at the end when you have a physical prototype to put drivers into. But through the dynamic simulators, you can actually get a response from your design and in the early days, validate it and make sure that once it's done, it's going to please the customer. So once again, for this one, we have actually more than one case study. The latest one was with Hyundai. They were actually trying to optimize lap times. It was more of a sporty type of application. But we have with Mahindra another use case, which was focused on improving comfort at a concept stage. So all of these cases that I'm mentioning, I will share them with you after this meeting. I'll make sure I send them to Benja and then he'll make them available for you. So that's it for Adams Real Time. One thing I would like to say, I will share this presentation as well, so you will have these links and QR codes. But because Adams Real Time is something that we're promoting very heavily, we have made in the Design and Engineering Innovation Showcase, which is an online conference that is publicly available now. We have a lot of content about this. We actually have interviews with the guys from JLG, Mahindra, and IDIADA, who are specialists in driving simulators, talking about their experience using Adams for this. And I highly recommend you that you look at that content if you think that this is something that can help you. And now we're going to the last bit, which is Adams for MBH. Like I said, this is not new to us. Adams has been used for MBH for quite a while. But you will see, well, let me mention something in case you didn't know that Adams is used for MBH. The reason why people don't know this sometimes is because Adams is time domain tool, okay, not a frequency domain tool. But what most people don't know is that Adams models can be linearized at any point in time. And once they are linearized, you can apply the typical analysis that you do in the frequency domain in order to understand the dynamic behavior of the system. In addition to that, Adam has the capability, especially through flexible bodies, to predict acoustic performance. So if you have a system like this one, the vibrations that are generated in the hub of this is a cut down version of a wind turbine. But the vibrations that I generated here, plus the vibrations or excitations generated in the gear train, will transform into sound that is propagated through the case of the gearbox. This is what we're looking at. And how that sound propagates is something that we can characterize via Actran. Normally, you would export this FE component into Actran and do that simulation there. But these days, we have embedded capabilities of Actran in Adams that allow engineers who don't have a lot of experience with acoustics to still define simple experiments, let's say, and essentially check the acoustic performance of the design. Now, the thing here is that this requires the model to be accurate at high frequencies, because sound, as we know, unlike vibration, it requires a higher level of fidelity in the model. So that is leading us to implement new capabilities. One of them, for example, it's this one, which is making rims in tires flexible. Okay, we'll move forward in this video a little bit because we're short in time, but yes, as you can see, the rims being flexible, obviously the flexibility of the rim compared to the flexibility of the tire means that from a functional point of view, this is not going to change the load dramatically, but it will introduce high frequency vibrations due to the stiffness of the rim that can be perceived as problems in terms of noise or in terms of comfort inside of a vehicle. So this implementation was made specifically in order to increase the frequencies that can be evaluated for suspension design. We also have introduced new capabilities. This just came up in the latest release, 2024.1, in order to get more information about the acoustic characteristics of bodies within the model. I know I'm rushing a little bit through this, but we're a little bit short of time now. We have introduced new capabilities for rotor dynamics at high speeds. Rotational components have a stiffening effect that, once again, it might not affect the functionality of the product, but it can introduce high frequency vibrations that are important to be considered for MBH analysis. Microgeometry. So in gears, if you don't know what microgeometry is, this is going to be very strange, but if you know what it is, gears in the face, they have small shavings. This could be just microns on the face of the gear to improve the contact between gear faces. And this tends to have a very strong impact on efficiency and MBH on gear trains. So in recent times, we always have, well, we always know, since we introduced gears in Adams, we've had the ability to model that. But we have introduced new methodologies for characterizing the stiffness of that contact that further improve the fidelity of the model, once again, with the intention of expanding the scope into MBH type of work. So before I move forward, as you can see, it's not a simple development that led us to do more MBH. It's at this point, when it comes to MBH, what we're doing is taking information from our customers about things that look little, but they are not. They are necessary in order to get accurate predictions of performance, and we're acting on those. So if you don't know much about Adams for MBH, I recommend you to talk to us because we can go very deeply into this topic. Or if you're already using it and you're finding limitations to doing more MBH with it, just talk to us, and whatever MBH you have might turn into the next implementation in the software, okay? I have a couple of use cases, but they are not directly related to these features because the features themselves are brand new, basically. But they just put the MBH analysis part of what we're doing in perspective, okay? We don't have time to cover them, but I will share them with you. You can read through them, and you will see good examples of very advanced applications of Adams for, in this case, vibration analysis for washing machines, acoustic analysis for motorcycles, vibration analysis for drivetrains. And these use cases, I'm sure, will put into context a lot of the things that I just mentioned. So with that said, and only 2 minutes to finish, sorry about that, we are done. I'm happy to take a few questions. I'm happy to stay a little longer if anyone is happy with that. And also, if you don't have time to make questions now and you want to send us an email, I'll be happy to take them away and get back to you.